Hey Data Junkies, welcome back. We are moving into our last topic module now for the One-Way ANOVA series, and this one's going to focus exclusively on effect size and power and how we can wrap up this with a strong finish here. So jumping right in, we're going to be talking about effect sizes, and with our effect sizes we use the French fry size for these, the small, medium, and large, and the effect size that we're going to deal with ANOVAs is R-squared. And we have another one in here called Eta-squared. These are going to be, if you hear these back and forth for one-way ANOVA, it's going to be the exact same score. They are equivalent to each other. They're calculated in the exact same way. Eta-squared, if you decide to pursue this a little bit farther and we go into factorial ANOVA, will branch off from its R-squared counterpart. But so long as we're dealing in one-way ANOVA land, R-squared and Eta-squared, dealing with the same thing here. And the definition that they have, they share a common definition. We're going to focus more on R-squared because that's going to carry over for when we work into regression as well. The definition for this is the proportion in variation from the total variance of the dV that can be attributed to the IV. That's a fancy textbook sort of way of saying, what is all the variation that could exist about a thing, and how much of it can we explain by knowing something about it? By knowing a characteristic, by knowing an independent variable, and the things we can measure from that independent variable, how much can we explain about the dependent variable? And it's talked about in terms of proportions or percentages, okay? The way we calculate it is taking the sum of squares between, and it's being divided by the sum of squares total. And that concept there, sum of squares between, that is the amount of variation that we can explain. And the amount total is the amount of variation total. So it's sort of a shorthand way of getting to that definition we just put there. Keep in mind when we're recapping back to ANOVAs, sum of squares within is also known as the sum of squares residuals or the sum of squares error. That's the stuff that we don't know. The stuff that we don't know plus the stuff that we can explain, the between, equals the sum of squares total. That's everything. This is where some of those things should be starting to connect and those light bulbs should be starting to go off a little bit. Now let's go ahead and see how this effect size works in action. Using the data from our Munchkins example with the differences in Oz and the complaints with the Wicked Witches, we have an R-squared equals your sum of squares between divided by sum of squares total. Pulling the data back from that example so long ago, the sum of squares between was 37.75. The sum of squares total is 56.95. I divide those up and I get an R-squared of 0.663, or approximately 66.3%. Using our French fry size scale, that is a large effect. We are able to explain about 66% of the variation in the number of witch complaints based on knowing in what regions those witch complaints are coming from. Let's pair this into one of the examples we had with the sidekicks. In the previous lecture, we had a bunch of sidekicks. They all started with the letter S, and they were all rated on a scale of 1 to 100 about how awesome they were. And so that we have a sum of squares between divided by sum of squares within, and that generates out for us. We didn't have the sum of squares total. We didn't do that one by hand. But when we do the ANOVA calculation, it gives us in the output the sum of squares between and the sum of squares within. I can add those together to get the sum of squares total. So then I take those numbers out, I do that little bit of math, and I get an R-squared of 0.4, or 40%. So we can explain about 40% of the variation in knowing how awesome a sidekick is by simply knowing which sidekick it is that we're talking about. The groups were the names of the sidekicks themselves. And this happens to be a medium-large sort of comparison here. So it's halfway between medium and large. And again, these are sort of soft values here. Now, when we're talking about how to use this in R, how do I go ahead and calculate these things in a computational way that I don't have to do the by hand math? Well, for that, we're going to change our language gears. We're talking about an Eta-squared. Remember, I said that these are the same values equivalently. Eta-squared is a function that lives inside the LSR package. So we install the LSR package, activate the library, and it gives us access to the Eta-squared function. Note the capital S in Eta-squared. Inside Eta-squared, we put in our AOV dV tilde IV. This is the function for the ANOVA, okay? Note this doesn't work with the one-way test, so if you have to go ahead and do it with the one-way test, you're probably going to have to do the by hand variation if you want to get the more accurate result. But in this case, if we can go ahead with using the classic one-way ANOVA, we can go ahead and plug it into Eta-squared. When I run that, in this case I'm running it with the Wizard of Oz Munchkin issue here, it gives me an Eta-squared and an Eta-squared dot part. The Eta-squared part means partial Eta-squared. It should be the same value for the most part as the regular Eta-squared. Don't worry about what the Eta-squared partial is at the moment. That's for when you carry it into the things like the factorial ANOVA, which we're not working on here. So what it shows by our calculations here is that we have an Eta-squared, or R-squared, since they're equivalent, of 0.662822, which is rounded to the same value that we achieved by hand. Now, if I want to go ahead and do the Welch's ANOVA, I just said a moment ago that the one-way dot test can't use the Eta-squared, R-squared version. We have a different by-hand approach. Unfortunately, I'm sorry, I don't have a function for you guys, but the Welch's ANOVA had to do some under-the-hood work on the degrees of freedom and things like that in order to compensate for the unequal variance. So in order to do that, I'm presenting you with an omega squared function here. It's a little bit of math, but it uses the degrees of freedom between, just the degrees of freedom between, your f-score and your total sample size. We plug those into a little bit of a function here, and it's going to generate for you an omega squared value, and we interpret the omega squared in the exact same way as your r squared and your eta squared there. Now, the omega squared, if you're looking for it, is not a very widely known or widely used value here. I'm producing it here for you for your information so you can work on these things, and there's a link in the slide if you want to go see a little bit more about this and what we're dealing with. Now let's go ahead and apply this omega squared to the example we had in the previous video where we were talking about the amount of credit that was being issued based on what kind of housing you had. So with that one, I'm reproducing the Welch ANOVA's results here, and it had an f-score of about 13.5, 2 degrees of freedom in the between, 92 degrees of freedom on the within, and a ridiculously small p-value. Note this example here had about 400 observations, so I'm going to plug this into the omega squared function, and when I get the math result out, it's going to be approximately 0.59, or about rounded 6%. So this is going to fall into what I call diet small size. Diet size small. It is smaller than our real small stuff here. So we can only explain about 6% of the variation in how much credit someone is being issued based on knowing their housing status, if they own, rent, or mortgage their homes outright. So that's kind of how we use these effect sizes here. Let's change gears to talk about power analysis. Now, like all of the previous power analysis from before, we're turning to the power library, the PWR library. And inside that package, we're going to get access to the pwr.anova.test. It follows a very similar naming logic to the other power analyses that came before it, power.norm.test, power.t.test, power.chi-square.test. This one is power.anova.test. Now, this one's going to have its own specifications that go inside of that, so let's take a brief look. We need to specify the number of groups. That's being identified as k. How many groups do you have in your independent variable that are being paired off? F, what is the effect size? For this, you can go ahead and plug in your r-squareds and eta-squareds or your omega squared, depending on how you're generating things out. The sig level, this is your alpha. Power, this is of course the power of the test. And n, this is the sample size per group. Do not put in the total sample size here. It's a sample size per group. And it's assuming you have equal sample sizes. If you have unequal sample sizes, put in the smallest sample size of all the groups you have. Okay? So if I had groups and they were ranging in sample sizes from 8 to 20, 8 would be the value I would put in here. Okay? Now, the rule of thumb when you're dealing with effect sizes is just to keep in mind when you're plugging them in that if you don't have an effect size and you're trying to generate one or you want to use it as an estimate, 0.1 for small, 0.3 for medium, and 0.5 and greater for large. Now I'm going to go ahead and use an example here with the Munchkin data that we had before. And like most power analyses, I specify 4 of the 5, and the 5th one I leave as null, and when I generate my power analysis, it's going to tell me that missing item from there. So in this case, I want to know what was the power of the test that we had from that example. Well, I had 4 regions of Oz, north, south, east, and west, so k is equal to 4. I had an alpha of 0.05, so I'm plugging in 0.05 as sig level. The the F, which is the effect size that we just generated before with the R-squared, was about 0.663, so I'm putting that in here. This should be as proportions, so if it's percentage, you have to convert it back. 0.663, n equals 5. This was the number of Munchkins I had in each region, and I had an equal sample size, and that sample size was 5. 5 in the north, south, east, and west respectively for a total of 20. So 5 goes in for my n. And I'm leaving power as null because that's what I needed to figure out. And it's going to report back that I have a power of 0.58 rounded. Now this, as we should know, is less than ideal for what we wanted. 0.8 is what we needed to get taken seriously. So I'm going to redo my power analysis, and I'm going to take out sample size, and I'm going to plug 0.8 in for power. And that's going to allow me to ask the question, at what sample size do I need in order to obtain a power of 0.8 given the number of groups, the alpha, and the effect size that I had before? And when I run that, that shows to me that I have a sample size of 7.256 rounded, and because we're dealing with individuals here, we're going to round up. So I would need a sample size of at least 8 in each group in order to get a power of 0.8 with these other values that I have here. Now let's go ahead and do another example here using the credit card analysis from the previous video. And in this case, I have the 3 groups, rent, own, and mortgage, and I have the same sig level of 0.05 for my alpha. I have a much smaller effect size that I have here. The effect size for that particular one was the 0.059, and I have the smallest sample size group was 28. That was the ones that had owned the homes. The others were like 180 something, so I'm only plugging in the smallest group that I have there, and I'm leaving power as null. That's the one I want to figure out. It generates out for me and says I have this very meager and small 0.53, so it's a ridiculously low power. I'm going to redo my power analysis. I'm going to reset it to plug in a 0.8 for my power, and I'm going to ask power analysis, dear power analysis, what sample size do I need in order to get the power level I want with 3 categories, a tiny effect size of 0.59, and an alpha of 0.5? And it tells me I need at least about 924 rounded individuals in each group of my sample. Much, much larger than what I had before. What's driving a lot of this was the fact that the effect size we had in here is so small. If we would have had a larger effect size, that would have given us more power and less sample size that we needed in this relationship. But that's going to kind of wrap up our talk on power analysis and effect size, and it concludes our talk on one-way ANOVA. Stand by for additional videos where I'm going to give you some walkthroughs inside R, and we're going to break some of these out. But outside of that, I'll see you all in our next module.